In the last lecture, you would recall we discussed two kinds of errors which creep into our observations. One type is called systematic errors. Let me remind you that systematic errors are caused by deficiencies in the measuring device or by defective design of the experiment or by personal biases of the observer. The deficiency in the instrument, for example, could be caused by a permanent shift in its zero or by non-uniform calibration of the scale. The defect in the technique could be that the temperature to be measured is such that the thermometer does not touch properly the body of which it is supposed to measure the temperature. Personal biases, example is that while reading a scale, your eyes may be always towards the left of the point to be read. All these cause systematic errors, and systematic errors, as I said in the last lecture, cannot be estimated. The other kind of errors are random errors. Random errors are unpredictable. Let me take an example. Suppose your teacher asks you to measure the length of your classroom. You take all precautions which are necessary to measure the length. Even then, if you measure the length 5 times, you would not get the same result. Sometimes, suppose the length is 5 meters, sometimes you will get 5.1 meters, sometimes 4.9 meters, and so on. Random errors can shift the result on both sides, higher side as well as the lower side. And therefore, random errors are more troublesome than the systematic errors, and therefore, we have to find out techniques to reduce the effect of random errors. And today, we shall talk about how to deal with random errors. Suppose during an experiment, we make n observations of a certain quantity, say length. Suppose the values we get are a1, a2, a3, etc., going up to an. Then the mean length, that is the mean of all observations, is a mean equal to the sum of all the observations divided by n. Each of the values of a deviates from the a mean. You see, for example, let us say you take mean of 6, 7, 8. The mean is 7. 6 deviates from 7, 8 also deviates from 7. So, each observation may deviate from the mean. Sometimes it may be equal to the mean, sometimes they deviate from the mean, and the deviation could be positive or negative. For example, 6 is smaller than the mean 7, therefore, the deviation is negative. 8 is larger than the mean 7, and therefore, the deviation is positive. But the sum of all these deviations from the mean would be 0. You can easily see why it should be 0. You see, let me go back to the formula of mean. Sum of a I divided by n. So, if you multiply n by a mean, you get the sum of all the observations. So, the deviation from the mean may be positive, may be negative, and the sum of all these deviations is 0. However, the absolute value of the deviation is not 0. That means, if the deviation is negative, we take the positive value. If it is positive, then we take the positive value. Suppose the deviation is minus 0.1, then we treat it as 0.1. If the deviation is 0.1, then it is fine. If it is negative, we make it positive. That means, we take the absolute value of the deviation, and their sum is not 0. the quantity by which a value differs from its mean, absolute value of the deviation is called absolute error. Here I have before you 10 observations of the time period of a pendulum whose length is 100 centimeters. The first column is just the number, the second column is time period in second, the third column is deviation from the mean, and the fourth column is absolute deviation from the mean. That is, in the last column all numbers are positive, in the third column numbers are positive as well as negative. In the first column there is just number, in the second column we have time periods, and at the end we have the mean time period, which is 1.99, and if we sum all the deviations you get 0, as I have been saying. But the sum of the deviations which are absolute, which are all positive, that sum is not 0. In this case that sum is 0.32, and if I take the average of all these deviations it is 0.03, and this 0.03 is called the absolute error in the mean 1.99. Here I repeat again, data of time period for a simple pendulum of length 100.0 centimeter is shown in the last slide. 10 observations were taken, the mean time period is equal to 1.99 seconds, absolute error is 0.03 seconds. The range of time period is 1.99 minus 0.03 to 1.99 plus 0.03, that is, the actual time period lies somewhere between 1.96 and 2.02. Let me repeat this again for your benefit, because this is very important. The absolute error in the mean is 0.03 seconds. This gives the range on both sides of the mean. If you add, this gives the higher side, if you subtract from the mean this absolute error, this gives the lower side. So, in this case the lower side is 1.96, the higher side is 2.02, and therefore, the actual time period lies between 1.96 and 2.02 seconds. Let me repeat what I have been saying for your benefit with the help of this slide. The sum of the absolute values of delta A I is not 0. We can therefore find their mean, and delta A mean is equal to the sum of all delta A I divided by n. Remember, we take absolute values of delta A I, which are all positive. Now, what is the implication of this? The implication is that the actual value of A will lie in the range A mean plus minus delta A mean. So, delta A mean determines the range around which A mean within which the actual value lies. For example, if A mean has a value 7 and delta A mean has the value 0.5, then the actual value of A will lie between 6.5 and 7.5. So, this determines the range, delta A mean determines the range within which the actual value would lie. Before I go to the next slide, I would like to point out that in the denominator of delta A mean there is n, and remember, n is the number of observations, and this will play a very important role. Notice that in the expression delta A mean equal to sum of absolute values of delta A I divided by n, n occurs in the denominator. Therefore, the range delta A mean can be made as small as you like by increasing the number of observations. Reducing delta A mean, that A mean can be made to approach as close to the actual value of the quantity being measured. Let me again try to repeat this in the following fashion. Your teacher has told you to take 10 observations, let us say in the case of a simple pendulum experiment, and the time available with you is much larger. So, I would suggest that you take 20 observations, if possible take 30 observations, and then you find the range. You will find as the number of observations increases, the range within which the actual value of G lies decreases. That means, you are approaching more and more to the real value of G, to the actual value of G. So, the number of observations for any experiment reduces the error in the experiment. Let me give you another example. Suppose you go from point A to point B by car every day, and suppose the distance is around 9 kilometers. Sometimes the meter on the car will show 10 kilometers, sometimes will show 9 kilometers, sometimes 8 kilometers, and so on. However, if you take 20 observations or 30 or 40 or even 100 observations, you will find that you can find the distance quite accurately. So, the number of observations decide how accurately you can find the result of an experiment. So, instead of absolute error, we can also define relative and percentage error. See here on the slide, relative error is delta A mean by A mean, and percentage error is delta A mean by A mean into 100%. Many times you have to think of errors in combination. Suppose you measure two quantities A and B, and delta A is the error in A and delta B is error in B. Then the maximum error in this sum A plus B is delta A plus delta B, and even if you take the difference A minus B, the error is still delta A plus delta B. That is why it is called maximum error. The error in A by B, A divided by B, or A multiplied by B, is delta A by A plus delta B by B. Whether you take the division or whether you take multiplication, the error is always delta A by A plus delta B by B. If delta A is the error in A, then the error in A raised to power n is n times delta A. For example, in the formula for finding the value of G, where G is equal to 4 pi squared L by T square, the maximum error in G, that is delta G, is delta G equal to delta L plus twice delta T. Notice that the time period contributes twice the error in T, whereas the error in L is just delta L. That means, time must be measured more precisely than the length. So, to conclude today's lecture, the random errors can be removed as much as you like by increasing the number of observations. Next time we shall take another topic, that of vectors and scalars.